Hello, welcome to Waves Part 1. Now, as in all our physics topics, let's just make sure that we realise that physics is everywhere. So where do you encounter waves? Well, everywhere, really. Water waves, you go swimming in the ocean, you get bobbed up and down, that's a water wave. Sound waves, you're hearing this right now, that's a wave. You might have warmed up some leftovers in your microwave, they're waves. Radio waves are out there, how you get your television, everything else, radio, all related to waves, and the mere fact that you can see things out here in the universe is another example of waves. So the characteristic of all these is that they all carry energy, and that's one of the parts of the definition of a wave, is something that can transmit energy. Another way of defining it is a disturbance or vibration that transmits energy without the transport of matter. So no physical mass has to be transferred, but energy can be transferred. And that's how, for example, you can hear the energy of sound is being transferred through a medium from one point to another point, but the medium itself, the air in this case, is not actually moving between point A and point B. It is moving, but it's not moving between point A and point B. And so we have a few different types of waves, and we're not doing a comprehensive course on waves, but we are going to touch on a few of them. The first type of wave is a mechanical wave, and that's an example of sound which we were just talking through, and that requires a medium to travel through. And so something like space, which is a vacuum, there's no sound. You have to have some sort of medium, and that medium most commonly is air, but it doesn't have to be air. It could be any gas. It could be a solid thing. So when you tap on something, for example, tap on a metal bar, the sound goes through that metal bar and comes out the other end. And the transmission is due to the vibration of the particles in the medium. Electromagnetic waves, which we'll look at in a lot more detail later on in the year, is an example of which is light, do not require a medium to travel through. They are self-propagating electric and magnetic fields, and therefore they can travel through a vacuum, and that's why we can get light from the sun, and we can also use radio telescopes to look at the electromagnetic radiation out there in the universe. Types of waves, well, they can be classified according to the motion of the particles in the medium if we are relating to a medium. And transverse waves, the particles vibrate perpendicular and to the energy flow. And an example is light. Although we're not talking about particles in terms of matter, we're talking about the vibration of electric and magnetic fields in the case of light and radio waves, but certainly in water waves it's a lot clearer. The water particles are moving perpendicular to the energy flow. So if waves are coming into a beach and you're sitting just outside the breakers, when the waves come through, for example surfers or yourself, you bob up and down as the wave goes through. You don't, and you might have a slight circular motion because that's how water waves work, but you don't catch each wave into the shore. It's only when they break that you can actually use some mechanical effects, i.e. a surfboard, to get transported to the shore. Generally waves just make you bob up and down. Longitudinal waves, now in these ones the particles vibrate parallel to the energy flow, and an example it would be sound waves. Now let's have a look at some diagrams just to explain what these guys look like. So here is a transverse wave. This is the energy direction, is going from left to right, and these dots represent particles movement, and you can see that the particles are all moving in different directions, but there is a pattern to their movement, and the pattern will form this wave. So particles are moving here perpendicular to the energy direction, which is left to right. And so if we move this particle on a little bit more, or move this wave on a little bit, just a quick pause when someone walked into the room. What was I saying? So if we look at this, this is a snapshot of the wave, for example, and this is a little snapshot a little bit later after the wave has moved a little bit. And you can see that here we're showing that these arrows represent the velocity of the particles, and they're always perpendicular to the wave motion. But this one's moving up, so if a little bit later it's actually here, and this one has moved up to here, and this one has jumped all the way up to the center line. And the particles do not always have the same motion. Like this particle will move up, and then it will move up to here, and then it will move down to here. I'll show you some animations that make a bit more sense than that. Rather than me dribble on, I'll show you some animations in a sec. Okay, but that's a transverse wave. A longitudinal wave, which is quite difficult to actually draw in a diagram. Again, I'll show you some animations in a sec. But let's have a look. This is, for example, a slinky, a great big spring, and we'll pull this out in class and have a look at it. Here you have a compression, so the spring is compressed a little bit, and it will move from, in this case, left to right, and the particles themselves are moving left to right as well as the disturbance, in this case a compression, moves through it. A bit hard to see in that diagram, but again I'll show you an animation. Another one, here's a metal rod. You hit at this end, it compresses the particles a little bit, and that compression moves all the way down the bar. That would be a longitudinal wave. Sound, here you have a tube, a speaker, an ear, and the air particles are compressed, and they move backwards and forwards, but they don't. The air particle here does not move all the way down to the ear. It just moves backwards and forwards with a limited range of movement, but the energy is transmitted in a longitudinal wave. Similarly, here's an earthquake or an explosion from an atomic test, and longitudinal waves spread out across and through the earth and can be observed, and we've talked about that in previous sections, how we look at earthquakes and the distribution of earthquakes. So some more terminology. So here we have a snapshot of a wave. On this axis we've got distance, and this one we've got displacement, so that's the movement of the particle. And we have here, the first term is a wavelength, which is given this little symbol here. A wavelength gives us the distance between two particles that are in phase. Now what do we mean by in phase? That means doing the same thing basically. So here we have a particle that's going to be moving down, and this particle here is also going to have exactly the same motion as well. Now they've drawn the wavelength here between two center point lines, but you could equally draw the wavelength between two crests, for example, where these guys are crests and these guys are troughs. That's pretty sensible. And so we can have a wavelength between two crests, but we could also have drawn a wavelength between two troughs, just to make sure that we are aware. Now the amplitude is the variation from the center line, or the mean position. And in this case that amplitude is equal to that amplitude, because this wave is symmetrical around the center line. And one cycle is just one repetition of movement. And that's the basic terminology that we have. Anything different in this one? Not really. Wonder why I showed that twice. It's a mystery. Here's a longitudinal wave, and in longitudinal waves we have a compression and then an area which is extended, which is called a rarefaction, and then another compression. And the particle motion is from left to right, and the amplitude will be half of the compression, because the particles move backwards and forwards only half that, which is similar to the transverse waves which we looked at just then. Now in a longitudinal wave, again the wavelength is between particles that are in phase. So if we take a center of a compression and a center of a compression, or the center of a rarefaction and the center of a rarefaction, they should give us the same lengths, which would be one wavelength. Here's another representation of a longitudinal wave. where they've just used bars, and the density of the bars gives you an impression of whether it's a compression or a rarefaction. And they use this one quite commonly because with sound, the variation is actually a variation in pressure, and so the compression will have areas of high pressure and the rarefactions are areas of low pressure, and that's what we actually hear because our eardrum is so sensitive to variation in pressure. So we could send a series of pulses down. Okay, now a pulse is a single wave, and then we can have a waveform which would be a repetition of a similar pattern, and so here we're having a repetition of pulses, and so we're getting a waveform. And again, they've tried to show here, this is what it looks like in a spring. So there's our compressions, and there's our wavelength and rarefaction compression, and this is trying to represent the density of particles, or another way of saying it, the pressure, or the air pressure if this was air. Could be pressure of a gas as well, any other gas. And so you see the particles are dispersed here and compressed here. So let's have a quick look. Let's see if I can bring up these animations. There should be one here somewhere. There we go. We want this one. Here we go. We'll drag this across. Okay, now this is an animation of a longitudinal wave, and there's a couple of red dots here. And if we watch a red dot, it's just moving backwards and forwards. It goes to meet a compression, and then once the compression moves through, it goes to meet the next compression, and so forth. And these are the wavefronts, and if you train your eye just to follow a wavefront, you can follow the wavefront moving from left to right, but the particles themselves are just moving backwards and forwards. So just rewind this and have another look at it. It takes a little while to get your head around what's happening, and this is how sound works in air. Now if we move down to a transverse wave, the particles, here's the waves being transmitted, but the particles are just moving perpendicular to the motion, backwards and forwards, backwards and forwards. Hopefully we can see that. We're more commonly, or more common understanding of these waves, these ones take, the longitudinal waves take a little bit longer to get your head around what's actually happening. Okay, and I think I also have another animation here somewhere. If I bring this up, here's an animation of a longitudinal wave where the compressions are just where the bars are closer together, and we can see the compression. I'm following it with my mouse now. It's moving along from left to right, but the bars themselves are just moving backwards and forwards around their mean position, which is shown by these dots. Okay, and that's how sound and longitudinal waves work. So let's get rid of that, and let's move on. Hopefully I haven't crashed the computer. So a couple of terminologies here. Phase, I've used that a couple of times. It's the stage of vibration that a particle has reached in its cycle of motion. Particles are in phase if they are moving in exactly the same manner at the same time. Wavelength, the distance between two consecutive points in a wave that are in phase. So make sure you understand what in phase means. Amplitude, the maximum displacement of a particle from its mean position. Frequency, the number of complete vibrations or waves per second. Frequency is in hertz, given the symbol F. Period, given the symbol capital T, the time taken to complete one vibration or to produce one complete wave. And the velocity is how fast the particle, or how fast the wave travels through the medium, not to be confused with the individual particle motion, which will have their own velocities depending on which way they're moving and how they're moving relative to the wave. So just reaffirming, we've pretty much done all that. We'll demonstrate that with a slinky. I'll bring that out and put that on the floor and we can have a look at that. Here we have a wave. We've got some definitions. We've got some points on the wave. And a couple of questions. So what I want you to do is pause it right here, read these questions and work out which letters correspond to these various stages. Alright, ready to pause? Pause. Okay, when I tell you, unpause. And I'll give you the answers. Right, the answers are those ones. So which particles are in phase? Let's see, N, where's N? N and U, because basically one way of thinking about it is to think about whether or not it's what's going to happen next. And N is going to move down because a trough is coming. So it's moving down to become a trough. U is moving down to become this trough. Q and W, Q is going to move up to become this crest. So is W going to come up and move this become that crest. What particles are stationary? Well, they're stationary right at this instant just here. Okay, where they stop moving up, and then like V and P have stopped moving up and they're just about to move down. S has just finished moving down and is now going to move up because it's now got to become that crest as the crest comes through. Which particles are moving up? Well, the ones that are going to become crests shortly. There's our answer. And which particles have the greatest velocities? Well, one way of thinking about this is the ones that have the greatest slope, because they've got to undergo the greatest change. So these are M, R, T and X. They have the greatest change to occur. And this is just showing how particles have moved. Q has moved from there to there. M has moved down from there to there because it's got to become this trough. Q's got to become this crest, and V's got to become this trough here. And if we were to draw, see, the displacement is actually varied, and so M has undergone the greatest displacement, and therefore it has the greatest velocity, because each of these has taken over the same time period. So that's just verifying our velocities as well. Now, sometimes graphs are given as different, have different x-axes. In this case, it has the time in periods. So that's one period there. So we have one wave in that period, and there's a 2 period. So we have a second wave, and again they have displacement here. Sometimes they're even given in angles, and the angles where one whole complete cycle is represented as 360 degrees. And so that's why it's drawn like that. And sine is an unusual axis to describe the motion, but remembering we can have waves described in a variety of ways. And I think I've shown you that little animation. Now there's a couple of equations we need to know that are on our formula sheet. We've got F, where F is the frequency in hertz, is 1 divided by the period, capital T, in seconds. And V equals, what's that one? Wavelength, lambda, and F frequency. So velocity equals the wavelength, lambda in meters, and frequency. So now you should be able to do the first lot of questions in your workbook. Aren't you happy? And in the next video we'll look at boundaries, superposition and interference. See ya!